In this video, I'm going to be working a multivariable calculus quiz over Lagrange multipliers. Okay, so this is where we're doing some constrained optimization. And so the first one is, in using Lagrange multipliers to minimize the function f of x and y equals x squared plus y squared subject to the constraint that x and y, or x times y equals 2, what's the value of the multiplier lambda? Okay, now that does, require you to do Lagrange multipliers kind of the way I do it, or the way we do it out of the textbook or the test bank for the textbook that I have used in the past. But what we do, I think it's pretty standard. Gradient of f being the function we're trying to maximize, or minimize in this case, is going to equal, well, lambda times the gradient of g. But the way I like to do it, I like to just write out the gradient of f. And so that's going to be fx, looks like 2x, and fy is going to be 2y, because x squared plus y squared is the function I'm trying to maximize. Now the constraint is going to be like g of x and y equals a constant, because that's going to give you a curve. That's going to be g of x and y equals x times y. Now this needs to equal lambda times the gradient of g. So I'm going to say that's what I'm about to do here. Lambda times the gradient of g. And so g is g of x and y equals x times y. And so gx will equal y and gy will equal x. Okay. And yeah, really just for Lagrange multipliers, I need a thicker highlighter. The key equation is gradient f equals lambda gradient g. I'm sure I emphasized that along the way, but we really just kind of need to start there. Okay, and so then it gives us a system of equations, and so I've got 2x equals lambda y, and 2y equals lambda x. And I'm going to be honest with you, it's not like I sat and thought about this afternoon after class and before I recorded this video. But I was talking to some people about this in class, and algebraically, I cannot explain to you how I know that x and y need to be equal. But basically, if x and y were not equal, then these two vectors would not even have a chance to be equal. Okay, because you switch the components. So even with a multiplier, there's just no way, unless that multiplier was 0, but that's just not the type of multiplier that we're interested in the Lagrange multiplier situation. And that would not be one of the answer choices in a multiple choice setting. So what we're going to say is well, suppose x and y were both equal, right? And say they were both equal to some other number, t. Okay, in that case, I could have 2t and 2t equaling lambda times, well, t and t, and then you could see that lambda has to equal 2. And, this is a interesting example, because I know algebraically it's out there somewhere. I could show that I could set lambdas equal to each other, but then we kind of end up with I think x squared equals y squared, and that would make me think that x could equal the negative of y, but that would not work. And I can see just looking at the original equation, gradient f equals lambda gradient g, that wouldn't work. Basically, I know lambda equals 2. I'm just going to move on. If you want some more discussion, I could, we could look at some actual values and look at some counterexamples, but I don't know what else to say about this one, so I'm just going to move on. We want to find the maximum and minimum values of the function f of x and y equals x times y. So that's going to be, the thing I'm trying to take the extreme of. And I'm just, we're not going to actually take this one all the way. I don't even know if we're not actually going all the way for any of these. We're just kind of doing some problems about Lagrange multipliers. If you did the homework, that was plenty, right? So gradient f is going to be fx and fy. So again, this x times y thing, fx is going to be y and fy is going to equal x. And then that's going to equal lambda times the gradient of g, where g is the constraint curve. So the constraint curve is x squared plus y squared equals 1,000. So this is basically the exact opposite of the other one. Lambda gradient g. But these work out really nicely, so that's probably why we like them for the test. So, okay, this is going to give me a system, And we soon encounter a system of m equations and n unknowns. I clearly did not write this one. A little more excitement than I usually have. What's the value of m times n? So, okay, what this is telling me is I know that y equals 2 lambda x, and also x equals 2 lambda y. And, usually what we do is we kind of like solve for lambda, set them equal to each other. That's one way that works oftentimes, but not always. And, what was I thinking? I lost myself. But either way, I've got x and y and lambda. That's 3 variables. And it said m equations and n unknowns. So that means n equals 3. I have 2 equations, and that's m. So m equals 2, so that means m times n is going to equal 6. Okay, now the last one is the maximum value of xy cubed. On the ellipse here, x squared over 6 plus y squared equals 1 occurs at a point x, y, where y squared equals k. Find the value of k. All right, so I'm going to tell you before we even get into this, we're just going to do the Lagrange multiplier method because it's constrained optimization. And this y squared, it's just going to fall out. It's just like we're going to get to a point where it's just going to be obvious what y squared is, and we won't have to like go all the way to the maximum actual value of xy quantity cubed. On the ellipse, we'll just be able to see what y squared is going to equal. So, just like always, maybe this time I will, kind of like emphasize, okay, we're trying to maximize this. This is going to be f, subject to, being on the ellipse. That's my constraint, which is g. So, gradient of f is going to equal, okay, the derivative of xy cubed. I actually think that this is worth taking off to the side, because this one's, I don't know, I could see people having trouble with this one. All right, so we deal with the outside first and the inside. It's a chain rule situation. So it's 3 times that thing squared times the derivative of the inside with respect to x, which is going to be a y. And the inside stays the same. All right, so that's going to be 3x squared y squared times y is 3x squared y cubed. Okay, so I'll report that. 3x squared y to the 3. Okay, then if I take the partial derivative with respect to y of the same thing, it's going to be a very similar outcome. It's just the derivative of the inside will be different. Okay, so 3 times this thing squared, and then the derivative of x times y with respect to y, well, that'll just equal x. So I multiply by that for the chain rule, and that's where I'm going to get 3x to the 3 and y to the 2. And that's the gradient of f. I'm not going to need this scratch work anymore. And that's going to equal lambda times the gradient of g. And I think the gradient of g is going to be much easier to find. Okay, the derivative of x squared over 6 plus y squared with respect to x is going to be 2 over 6 times x, so that would be 1/3 of x. And then the derivative of that with respect to y is going to be 2y. What I just did there, that was lambda times the gradient of g. And so now I'm going to end up with a system. I'm going to have 3x squared y to the 3 equals 1/3 of lambda x. All right, and then I'm going to also have, I don't know why I was tripping over that. 3x to the 3, y to the 2 equaling 2 lambda y. All right, now I think what I'm going to do on both of these is just solve for lambda. All right, now I had a little brief pause about dividing both sides by x or by y, because what if I just divided by 0? But if you think about looking at these equations, if either x or y is equal to 0, then the other one would have to equal 0, and I would not be on the ellipse anymore. So I'm going to freely divide by both x and y. So on this one, I'm going to have, multiply by 3, that would be 9, divide 1 power of x away, so that would give me 1 power of x, and still 3 powers of y, and that will equal lambda. With this one, I'm going to say, all right, divide by 2, 3/2, and divide by y, so that would be x to the 3 multiplied by y to the 1. That's going to equal lambda. Now, what I want to do here, or what I did when I worked a problem very much like this, but not exactly this one, I think what I did was I divided one equation by the other, and I ended up with by like solving for y squared that way, but then I ended up with something in terms of x. And a student tipped me off today that I think if I set the two things equal to each other, that it might go a little bit better for me. Actually, I think it's going to end up with something equivalent. It's all good though. I might say, all right, 9xy cubed equals 3/2 x to the 3y. Okay, and I'm only interested in the value of y squared. So I should definitely divide both sides by 1 power of x. And so, because I already did it once, so 9y cubed equals 3/2, and then I'm going to divide, wait a second, I'm dividing both sides by 1x and 1y. So I should have like lost power there. So 9y squared equals 3/2 of x squared. And maybe I will divide both sides here. Oh, wait a second, I see it. Yeah, I am going to divide both sides by 9, and I'll get y squared equals 3 over 18 is 1 over 6x squared. It's like, what do I do with this? But it's like 1 over 6x squared. That's exactly what I'm seeing up here. So maybe I need to go back there. And it's like, oh yes, I'm on the constraint curve, so that equation has to be true. So I'm going to say, all right, back to this one. Let's see, from here, whoops. Let's see, this. I'm going to say x squared over 6. That's now equal to y squared. Y squared plus another y squared is going to equal 1. So that means y squared is going to equal 1/2. And I'm going to get y equals the square root of 1/2. Nope, I don't even need that. I was looking for the value of y squared, and that is equal to 1/2, and there it is. It just happened. Okay, so that's kind of what I remember happening from before. Okay, so that was a nice little Lagrange multiplier quiz that didn't actually require us to go through and like solve one all the way out, and that's kind of representative of what you're going to have to do on the unit test here in my class for multivariable calculus. So that's going to be all for this video. Thanks for watching.